Welcome. The acyclic chromatic number of a graph is the minimal number of colors one can use to color the graph such that every Kempe chain is a forest, doesn't have any closed loops. This is a notion which I only recently saw in the literature. There is a theorem of Hakimi MItchem and Schmeichel which relates this with the star number of a graph, which is the minimal number of star forests one can use to cover the edge set of a graph. So I have here a couple of definitions. They're all packing problems or covering problems. Actually, these are all packing problems. And the chromatic number, that's a well-studied number. The arboricity also, the minimal number of forests one needs to cover the edge set of a graph. And then this is the acyclic chromatic number, which is the minimal number of colors such that all Kempe chains have no loops. This is something I really kind of bothered with for many weeks now, and I talked about this result that we can, every non-prism planar graph, we can color in such a way that all the Kempe chains have no closed loops, which means we actually proved that this acyclic chromatic number is smaller or equal to 4 for all planar graphs. Actually, I proved it for 2 spheres, but if you have 2 spheres, then it's by maximality. This is true for every planar graph. And then I used these Kempe chains to actually get the information about the arboricity, to get the arboricity of G smaller or equal to 3, because what you have, if you have 4 colors, you have 4 over 2, binomial 4 over 2, 6 different Kempe chains, and these Kempe chains can be grouped into 3. And so what I did, and so we have 3 different types of forests. And I used this also in 3 dimensions, 8 colors to acyclically color a 3 sphere. Then we would also have 8 forests. We would have the arboricity 8. So it's very interesting, this relation between chromatic number and arboricity, especially because I see that the chromatic number is bound in a polynomial way. That's what I proved for manifolds, and the arboricity explodes like exponentially with the dimension. So it's completely different thing. But in the case of the acyclic chromatic number, we have a close relation, and that's what I kind of used. And I saw in the literature now that Hakimi MItchem and Schmeichel, Hakimi is an Iranian mathematician, he's passed away, but in 1996 they proved in general that the star arboricity, so if you cover by stars, that's of course also forests, stars are forests, then you have this relation. Now you can look at all kinds of different forests. For each type of forest you have a partition problem. You can look at dominoes, it's a popular covering problem. You can look at linear graphs. Linear graphs is a famous open problem about the linear arboricity of a graph, depending on the maximal vertex degrees. And then we have trees, forests, and these are star graphs. In chemistry, a star graph, for example, is the methane, or the linear graph is the water. And if you have molecules, you have this caterpillar graphs. Caterpillar graphs are graphs such that the non-leaves, if you look at the non-leaves, this is a path graph. So because every domino graph is a linear graph, and every linear graph is a caterpillar graph, and every caterpillar graph is a tree, so you have this relation. This is an obvious relation. You have also the relation between stars and arboricity. I like that relation because it relates arboricity. Essentially, it doesn't matter up to a factor 2 whether you cover with stars or whether you cover with forests. And the reason is, of course, if you take a forest or you take a tree, you can cover it with two type of stars. One type, second type, again 1 second. So you can, because you can color a tree with 2 colors, you can also cover a tree with two type of forests of stars. So this is immediate, and this is less obvious here that we have this relation between the star, the star arboricity and this acyclic arboricity, but it follows from that immediately using the lemma, it follows that arboricity is bound above by the acyclic chromatic number. This is a result of Hakimi MItchem Schmeichel, and actually I can prove a little bit more, and just going directly to the arboricity and show that the arboricity is smaller or equal than the acyclic G-1 if it is even, and if it is odd, then we have that bound here. So if it's even, it's a little bit better, and that's what happens here, right? It was even, so 4 minus 1 is 3. That's why you need 3 forests if you have 4 acyclic colors, if you can use 4 colors such that the Kempe loops don't form any, Kempe chains don't form any loop. And the proof is, quite obvious. What you can do is you can just look at the Kempe chains. So what type of Kempe chains you have? If you have C, if C is this number, of colors which you need to acyclically color the graph, then we have this number of Kempe chains, and they are all different. You can take this pair or this pair, this together, you can lump together to one type of forest. And then so we can divide by C half pairs, and then we lump them together, and then we get just C-1 forests. In the case if it's odd, we lose one. We have kind of just a fifth wheel at the wagon, right? If we would have 5, we would have a fifth wheel at the wagon. We could not pair it with something else. We would lose a little bit, but it's still C-1, and that's actually then a C, and that's this corollary which was known. So it's an interesting question. Also, I have not yet an example where this is not true for the lower bound. We can take acyclic G-1. So I actually guess there is an example where it doesn't work. For example, you would have to look at some graph with chromatic number, acyclic chromatic number 5, and then see whether we can actually get the counter example. But I don't have an example yet here. Also in that paper, there's this mentioned again that the arboricity of a planar graph is smaller or equal to 3 without reference and without proof. So I guess there must be some kind of easy argument. This is an exercise in the book of Bondimurti, but there must be some, obvious. It must be somehow obvious to these guys why the arboricity of a planar graph is smaller or equal to 3. I don't see that yet, and it's they make the impression that it follows from the Nash-Williams formula, but I don't see that it follows from the Nash-Williams formula, and I don't yet know. So that's kind of an interesting question. That's an interesting question. And I also battle still with the question in the barycentric limit to prove really that this is a linear algebra problem, that the arboricity really explodes exponentially with the dimension. So that's it for today. you.